Welcome to the FEKO Tour. This tour is an introduction to the features and wide range of applications of FEKO. What is FEKO? FEKO is a state-of-the-art electromagnetic simulation tool. Numerical methods are used to simulate real-world applications. FEKO provides several numerical methods, each suited to a specific class of applications. FEKO is applicable to radiation, coupling, scattering, and waveguiding problems. Such applications range from geometrically complex to electrically large. No single numerical method can handle the whole range of application efficiently, which is why FEKO offers a range of methods. FEKO is used for a wide range of applications. Many different classes of antennas can be analyzed with FEKO. For example, wire antennas, reflectors and horn antennas, wideband antennas, and microstrip patch arrays. FEKO is widely used for antenna placement analysis, as it is ideal for solving electrically large structures. The hybrid methods in FEKO allow for the analysis of geometrically complex details on electrically large platforms. FEKO can be applied to many electromagnetic compatibility problems. For example, modeling of measurement setups, shielding and resonance characterization, and cable coupling. The various numerical methods in FEKO can address diverse scattering applications. The method of moments and multi-level fast multipole method are ideal for highly accurate radar cross-section calculations. In this example, the accuracy of the MLFMM is verified by comparison with a published measurement. Physical optics and ray-launching geometrical optics are well suited to the solution of RCS for large targets, such as this F-35 aircraft. In FEKO, the finite element method and finite difference time domain are well suited to modeling complex waveguide junctions. For microstrip components, the method of moments and finite difference time domain methods are suitable. These examples show waveguide junctions and filters, transitions, and microstrip circuits, including a split ring resonator filter, a series inductor, and a coupler. FEKO is used in various industries. In the aerospace industry, FEKO finds many applications. For example, modeling a complex microstrip patch antenna array mounted on a satellite, an air traffic control antenna on a commercial aircraft, a microstrip patch antenna at 4.3 GHz mounted on a military aircraft, and modeling coupling between aircraft-mounted antennas. In the marine industry, FEKO is used for applications such as radiation hazard analysis, antenna placement studies, and radar antenna performance assessment. FEKO is also widely used in the automotive industry for integrated antenna modeling, considering coupling with cable bundles, analyzing windscreen antennas, and for exposure studies such as radars and SAR analysis. In the biomedical industry, FEKO is used for antenna design for body-mounted or implanted devices, local or peak spatial average SAR calculation, and the design and safety of MRI systems. FEKO offers a sophisticated GUI which supports both Windows and Linux operating systems. The FEKO GUI consists of two main components, CADFEKO and POSTFEKO, with easy workflow. CADFEKO is used for geometry modeling and to set up the solution. CADFEKO has comprehensive parametric CAD creation features. CAD models and meshes can be imported and exported. CAD healing features can be used to repair imported CAD. A scripting interface allows the automation of model setup with customizable dialogues for user interaction. POSTFEKO provides a graphical post-processing environment. Numerical results can be compared with imported measured data. Numerical results, graphs and images can be exported. And reports can be created in PDF, Microsoft PowerPoint, and Microsoft Word formats. Additionally, Lua scripting can be used to perform advanced, user-specified post-processing of numerical results. And now for a FEKO demonstration of a horn antenna. The basic workflow is to begin with the Construct tab and work through the tabs from left to right. The horn is designed for the L band, so we will work in centimeters. Set the model unit to centimeters. To create the waveguide of the horn, we will use a cuboid. We choose the second definition method and change the default dimensions of the cuboid as shown. Note we use mathematical expressions, but if we want a parametric model, we can also use variables. Set the label to Waveguide and click Create. On the View tab, click on Zoom to Extents to see the whole cuboid. Next, we create the flare of the horn. First, we set the base center. By pressing down and holding Ctrl and Shift, we can snap the origin of the flare to the face center of the cuboid as shown. Then snap to the two edges of the cuboid to enter the bottom width and bottom depth. We enter the rest of the dimensions manually. Then zoom to extents. To ensure that a proper mesh connection is made later, we must make a union of the different parts. Select all the parts in the tree and on the Construct tab, click on Union. The aperture of the horn is still closed, so we select the face shown and delete. Do the same with the face at the junction between the waveguide and flare. The geometry needs no transformation, so we skip the Transform tab and open the Source Load tab. The horn will be excited with a waveguide port. Flip the horn on its back. Click on the back face of the waveguide in the 3D view and create. We then add a waveguide excitation on this port by clicking on Waveguide Excitation. We only want the fundamental mode excited, so we use the default settings. Now restore the isometric view by selecting this icon on the View tab and then zoom to extents. The frequency must still be set. On the Source Load tab, click on Frequency and set a single frequency of 1.645 GHz. The next stage of the model setup is the output requests. On the Request tab, click on Near Fields. We will use a Cartesian coordinate system to calculate the near fields in the aperture of the horn. Enter the start and end coordinates as well as the number of field points. Note that near field points should not be requested exactly on mesh elements. Also request far fields. Click on 3D pattern for a quick selection and create. We can hide the field requests by right-clicking on them and selecting Show Hide. When the geometry is a few wavelengths in size and uniform, such as this horn antenna, we can save computational resources by using higher order basis functions, or HOBF. This can be activated on the Solve Run tab and then Solver Settings. Tick the box Solve MOM with higher order basis functions. We are now ready to mesh the horn. On the Mesh menu, click on Create Mesh. We create a standard mesh. CADFEKO meshes the geometry according to the wavelength. Users are advised to familiarize themselves with the meshing guidelines as given in the FEKO User's Manual. Now we can run FEKO from the Solve Run tab. FEKO provides a standard output during the solution process. It is important to note any errors or warnings. They must be corrected by going back to CADFEKO. Once FEKO has finished, we must run POSTFEKO for post-processing. We will view the near fields in the aperture of the horn. On the Home tab, click on Near Field and select Near Field 1. If we want to see a graph of the far fields, first select the type of graph. This will be Cartesian. Then click on Far Field and select Far Field 1. To wrap the graph, on the result palette on the right for independent axis, select Theta Wrapped. To view the other principal plane pattern cut, right-click on the Far Field 1 trace and select Duplicate Trace. Then change the phi angle for the second trace to 90 degrees. To see a polar graph, go to the Display tab and select Polar Copy. That concludes the demonstration. Now for a more detailed overview of the numerical methods available in FEKO. As noted before, no single method can address all applications. This is why FEKO offers multiple solution methods. Methods for geometrically complex problems. Methods for electrically large problems. And hybrid methods for problems which are both large and complex. The method of moments is very well suited to radiation and scattering analysis. FEKO offers a fully featured method of moments implementation. It is applicable to metal surfaces and wires, dielectric coatings and sheets, dielectric bodies, and infinite planar media. FEKO provides ACA acceleration to increase the computational efficiency of the MOM. Higher order basis functions can also be used to reduce the memory requirements for certain types of problems. Low frequency stabilization is used for very low frequency problems. The MLFMM is an alternative implementation of the method of moments, working with a factorized version of the matrix. The MLFMM makes no physical approximations and is just as accurate as the method of moments. For electrically large structures, the MLFMM is orders of magnitude more efficient than the MOM. In this example, a satellite with integrated 106-element patch antenna array is solved in 9.8 GB with the MLFMM, while the MOM would require 896 GB, a massive computational cost saving. The finite difference time domain method is based on voxel or cuboidal volume cell meshing. It is well suited to modeling complex inhomogeneous regions. The FDTD is efficient for solving wideband problems. The finite element method is based on tetrahedral volume meshing. It is well suited to modeling complex inhomogeneous regions. For such problems, it is very memory efficient. The hybrid FEMM combines the two methods to yield higher computational efficiency than achievable with either method on its own. The hybrid MLFMM further extends the range of applications to complex dielectric regions in the presence of very large structures. Physical optics and large element physical optics can be used to solve problems involving reflections of metallic and dielectric bodies. PO is only applicable to electrically large structures, but these structures can have complex shapes. PO is extremely memory efficient. The hybrid MOM-PO combines the two methods to solve problems too large for any single method. Use the MOM for small details and PO for large structures. For example, when modeling an antenna mounted on an aircraft. For electrically larger structures, the MOM region can be solved using the MLFMM and the PO region using large element PO. Ray launching geometrical optics is based on shooting and bouncing of rays. RLGO is only applicable to electrically large structures. It can solve for multiple reflections of metallic and dielectric bodies and transmission through dielectrics. The hybrid MOM-RLGO combines the two methods and is typically applicable to antennas illuminating large structures. Use the MOM for small details and RLGO for large structures. This approach is extremely memory efficient. The uniform theory of diffraction is based on ray tracing. The UTD solves for reflections, diffractions, and multiple ray interactions. The hybrid MOM-UTD combines the two methods and is typically used for antenna placement analysis. Use the MOM for antennas and the UTD for electrically large, faceted metal platforms. This is another extremely memory-efficient approach. Now for an overview of productivity features, which add value to the numerical methods in FEKO. Extensive optimization capabilities are available in FEKO. Any model parameters can be optimized as FEKO supports parametric modeling. A wide range of optimization algorithms is provided. Any observable result can be used in the specification of an optimization goal function. Live monitoring of the optimization process is possible in the GUI. In FEKO, a problem is solved at a specified excitation frequency. A frequency response can be obtained by regular sampling over a frequency range. However, this can be very time-consuming. Adaptive frequency sampling provides a very efficient alternative. The AFS approach is based on sparse sampling with intelligent interpolation. AFS reduces the number of required samples dramatically and yields a continuous frequency response result. Circuit co-simulation allows for the inclusion of lumped linear circuit models in the electromagnetic field simulation. FEKO supports SPICE models, SZ and Y parameter blocks. Touchstone file import and export is also available. In this example, circuit co-simulation is used to reduce the computational cost of analyzing an antenna with complex planar feed network. FEKO can be used to evaluate the coupling between arbitrary structures and cable bundles. Fields for coupling from external geometry are rigorously modeled with the MOM, while the cable bundles are modeled with multi-conductor transmission line theory. FEKO supports various standard cables and user-defined cable bundle configurations. The domain Green's function method, or DGFM, is a fast method for solving large finite arrays. The analysis is based on solving one array element at a time. Mutual coupling is accounted for when calculating the self-interaction matrix of the array element by using a different Green's function for each element that accounts for the array environment. Computational complexity therefore scales according to the number of unknowns in the array element and not the problem as a whole. It is also possible to derive the far fields of very large arrays from the periodic boundary analysis results of an infinite array. This works very well for large arrays. The DGFM is more accurate and should be used for small to medium arrays. FEKO can analyze infinite periodic structures by solving only the periodic unit cell. Analysis options include infinite linear array structure, infinite planar array structure, approximate finite array results, comprehensive excitation phase options, and plane wave excitations. Applications include frequency selective surfaces, large finite arrays, and metamaterials. FEKO has a built-in solver that calculates the characteristic current modes of a structure with no need for post-processing by the user. Characteristic mode analysis allows for a systematic computational electromagnetic design approach and can provide physical insight into the radiation properties of a structure. CMA can be used to determine the resonating frequency of specific modes and to determine the optimum feeding arrangements to excite these modes. The three modal current distributions shown were calculated during the design of a mobile phone antenna for the 1800 MHz LTE band. CMA was used to analyze the structure, and slots were cut in the areas with weak currents, yielding the antenna shown on the right. In addition to its fast and efficient methods, FEKO offers various high-performance computing solution options. The FEKO solver is fully parallelized and is optimized to make full use of multi-core CPUs. FEKO is also optimized to fully exploit multi-CPU shared memory resources and is often used on large-scale clusters. FEKO supports graphics processing unit-based acceleration for certain solution phases. Finally, FEKO offers an optimized out-of-core solver to make efficient use of secondary storage when RAM limits are reached with large problems. This concludes the FEKO Tour. FEKO is developed by EMSS, with offices in South Africa, the USA, Germany, and China. It is globally distributed and supported through a worldwide network of representatives. For more information, please visit the FEKO website.